Hello everyone. Today I want to talk about doing saturation height modeling within Danomics. So saturation height modeling allows you to use things like capillary pressure data to evaluate your free water level and the saturation profile within your rocks. To do this in Danomics, it is a two-part operation. The first part involves processing your raw imported data that you would get from the vendor. And the second part involves making interpretations around that data. So let's get started. The first thing you'll need to do is you'll need to bring the data into the platform. So to do this, it'll just be File, and then you'll upload points. And these points are structured as follows. So you'll have an API column because that's how we tie well data together. You'll need to have a depth column because that's how we tie the data to a specific depth. Optionally, you may need to have a sample column. If you only have one capillary pressure data set per depth step, then your depth and your sample can be shared. Otherwise, you'll need to have a separate sample column. Then we'll need to have, of course, our actual capillary pressure data, the saturation from the sample, the porosity, and the permeability. Now what you'll notice is the porosity and permeability are repeated on each line for this sample. You'll only have typically one measurement for each capillary pressure sample. We just need to repeat that on every row so that we have a complete data set. And you can load this for as many pressure steps per sample as you would like. You can have as many samples per API you would like, and you can have as many APIs as you would like per points data set. So once you have your data in, you'll then need to run a flow, and this flow will consist of three tools: a points input tool, where you'll select the points that you imported, a saturation height tool, and this is what will actually process the data. You'll essentially just play match the columns here and match API to API, your sample ID to either depth or your sample, depending on how you imported the data. Then you'll choose your capillary pressure data, the saturation columns, porosity, and permeability. You'll tell us what type of measurement it is, whether or not it's mercury injection capillary pressure data or porous plate or centrifuge data. And then you'll enter some parameters for your fluid type and your hydrocarbon or brine density if you need to. And then finally, you'll give this an output name. Once you run the flow, this will only take a few seconds, and then you'll get the results as follows. Here you'll notice that we have the original input columns as well as a number of columns that were generated by the flow tool. These include things like our laboratory based saturation, a normalized saturation, our irreducible water saturation, our capillary pressure with reservoir fluids, our lever J with reservoir fluids, a height above free water level, our rock quality index, and you'll notice that we have duplicated the permeability column. This is to ensure that we have a consistent naming once we move this points into our CPI. So once you've ran this step, you're now ready to bring that data into your petrophysical interpretation. The first thing you'll need to do is you'll need to click on a well to activate it. Then you'll come here to the central drop-down menu and you'll select the saturation height modeling module. Once you've done that, you'll be greeted with this display and this parameter interface. And additionally, you'll have three specific crossplots that are pre-made for you for this type of interpretation. These are your irreducible saturation versus permeability, your lever J versus normalized saturation, and your irreducible saturation versus your rock quality index. Okay, so the first question you'll probably have is, how do I get this data into my petrophysical interpretation? There are two ways you can do this. You can either bring the data in as your optional core points here, or you can bring the data in using this drop-down selection menu that is available in the crossplot. Either one will work fine. Once you do that, you'll want to select your formation, and then you're ready to start adjusting these crossplots. So for each of the crossplots, there are corresponding parameters here within our parameter table. And here we're only looking at it for one formation. We only have the capillary pressure data for one formation in this well, and that's for the Parkman formation. And as we go through, we'll want to adjust these parameters. So starting off with our irreducible saturation versus permeability, we'll notice that we have an A parameter and a B parameter for this crossplot. A is the intercept, and B is the slope of this line. And you'll notice this is a log plot, and we're using a power law relationship for this. So as you increase the A parameter, that will move this line up. As you decrease it, it'll move it down. A more negative slope will give it a steeper trend through here. So for example, if I move this to, let's say, 0.38, you'll see the line move down. If I move it up to 0.45, we'll see the line move up. I'm going to set it a value of about 0.42. Similarly, if I adjust the slope, here we can see it becomes steeper. Here we can see it becomes shallower. And then we can put this at our final value here. So that's how it works for the irreducible saturation versus permeability. For the irreducible saturation versus RQI, it works exactly the same. You'll notice a slight difference here when we go to the leverage A versus saturation, the normalized saturation. Essentially here, what we're trying to do is fit a tangent to this line. So it still works the same, where the A parameter moves our data up and down, and the B parameter adjusts the slope. However, when we're interpreting this data, we're going to try to make this line so it's a tangent to the trend of our data in this case, as opposed to a fit to our data. All right, so that's how we adjust those parameters. Other parameters we'll need to set include our hydrocarbon density and our water density. And essentially, you want these parameters to match what you process through your flow tool. Otherwise, you open yourself up to inconsistencies in your interpretation. And then finally, you'll want to set your free water level. So here we have the sands that we pulled our capillary pressure from up at around 7,700 to 7,800 feet. Let's say we put our free water level at around, let's say 8,000 feet. The response we'll see here is that our predicted saturations are significantly higher than the saturations that we estimated from our typical water saturation interpretation. As we increase the free water level, so as we push that free water level deeper, we'll see these two interpretations start to converge. Until finally, we see a very close match between these. You'll notice that this only holds up in the sands, and that's because that is where this data is from. This data specifically is telling us about the response of this rock type to the saturation response. Here in the deeper interval, we're probably looking at a different sand facies, and that's why we're not getting an ideal match. So once we have done that, we now see that our free water level is around 8,500 feet in this well. That's significantly below where we are looking at. If this is correct, it would tell us that we could drill significantly down dip and still encounter a hydrocarbon column. All right, so that's it for a quick look interpretation of our saturation height modeling using capillary pressure data. If you have any questions, please feel free to reach out to me at support@danomics.com. Thank you for using Danomics. Goodbye.